Honors Chemistry, Unit 3, Bonds, James Bonds Review. You can access this review and this video at srhschem.wikispaces.com or on YouTube channel LEFFELlabs. First question asks us to construct a Lewis diagram for carbon dioxide and carbon tetrachloride. So first, before I can draw the structure of the molecule, I need to figure out how many valence electrons each of the atoms in this molecule have. So carbon dioxide is 1 carbon and 2 oxygens. So if I check my table of elements, carbon is going to have 4 valence electrons, and each oxygen is going to have 6 valence electrons. So I'm going to go ahead and put my 4 electrons around carbon. And this means that since carbon has 4 unpaired electrons, that it can make 4 bonds. Oxygen has 6 electrons, 1, 2, 3, 4, 5, 6. So because oxygen has 2 unpaired electrons, that means it can make 2 bonds. And the same will apply for the other oxygen. Next, I got to figure out which of these 3 atoms is going to be my central atom. So the central atom is going to be whichever one has fewest valence electrons, but never hydrogen. So in this case, carbon has 4 and oxygen has 6. So my central atom is going to be carbon. And to that central atom, I somehow have to connect 2 oxygens. So for each oxygen, I'm allowed to use 2 bonds. I have to use up those 2 bonds. So there's 2 bonds to connect that oxygen to that carbon, and same thing on the other side. Now if we check carbon, carbon has 4 bonds drawn, which is what we said we should get. So these double bonds are going to be a total of 4 electrons in each. So half of those 4 are going to come from carbon, and the other half will come from oxygen. And same thing on the other side. So for carbon, I've drawn 4 blue dots, which is what we should get. That's what we said carbon would have. And for oxygen, I've only drawn 2. So those 2 electrons that I drew, those are those 2 that are the unbonded electrons. So the other 4 electrons, because we're supposed to have 6 total, the other 4 electrons are lone pairs on the oxygens. So carbon tetrachloride has carbon and 4 chlorines. So if we check our table of elements, carbon has 4 and chlorine has 7. So I'm going to go ahead and put my 4 electrons around carbon, which means carbon can make 4 bonds because there's 4 unpaired electrons. And same thing for chlorine, except there's 7. So 1, 2, 3, 4, 5, 6, 7. So chlorine has 1 unpaired electron, which means it can make 1 bond. And the same will apply for the other 3 chlorines. Next, I got to figure out my central atom. So again, it's whichever one has fewest valence electrons, but it will never be hydrogen. So carbon is my central atom, and I've got to somehow attach 4 chlorines to that carbon, and each chlorine is only allowed to make 1 bond. A single bond is going to be 2 electrons, so half of those 2 are from carbon, and the other half are from chlorine. So of the 2 electrons, 1 from carbon, 1 from chlorine. So at this point, I've drawn carbon's 4 valence electrons, so I'm good there. But I've only drawn 1 valence electron for each chlorine, and chlorine is supposed to have a total of 7. So I already have 1, which is that unbonded electron, and now I've got to add the other 6 electrons, which are going to be lone pairs on the chlorines. Now that I have my Lewis dot structures all drawn out for carbon dioxide and carbon tetrachloride, I can look at what's the shape of these different molecules. So for that, we use Vesper theory. And if we look at Vesper theory, we have to check the central atom. So central atom is carbon, and it has 4 valence electrons, which are all in bonds. So there's no lone pairs on that carbon. There are 2 bonding atoms attached to that central carbon. So if I look that up on my Vesper chart, I see that that corresponds to the shape of linear. Next, for carbon tetrachloride, again, carbon is my central atom, and all 4 of its valence electrons are in bonds. So there's no lone pairs on that central carbon. there are 4 bonding atoms on that central atom. So that corresponds to the shape of tetrahedral. Next question asks us how many electrons are in each type of bond. So a single bond, such as that between hydrogen and chlorine, is 2 valence electrons. A double bond, like that between diatomic oxygen, is 4 valence electrons. So half of them come from one oxygen and half of them come from the other oxygen. So that's 4 electrons total. A triple bond, like that between diatomic nitrogen, is 6 valence electrons. So 3 from one nitrogen and 3 from the other. So triple bond is 6 electrons. You can think of each of those lines as being 2 electrons. So if there is 3 lines, that's 6 electrons total. Next question asks us to predict the boiling point. In other words, which of these pair is going to have the higher boiling point. So this involves using intermolecular forces. So these are the attractive forces that are between 2 different molecules. So I could have molecule A of water and molecule B of water, but I need at least 2 molecules in order for there to be intermolecular forces. So there's 3 types. The first is dispersion. So dispersion occurs in anything covalent, and you know something is covalent by checking to see that it's all nonmetals. Dipole-dipole is going to be something that only occurs in things that are polar covalent. So you can tell that by the molecules being asymmetric, or if there is a large electronegativity difference between the atoms. Hydrogen bonding is where we have hydrogen bonded to an FO or N bond. There's a big electronegativity difference between those bonds, so that kind of is like a polar bond. It is polar, but it's a special case where we have hydrogen bonding. So first molecule that we have is going to be methane. So the more intermolecular forces that we have, the stronger the attractions between those molecules and the higher the boiling point will be. So for the first one, I've got just dispersion forces. It's covalent, but it isn't polar. If I cut it in half, it's the same on both sides. And it doesn't have the H attached to F, O, or N. So all we have is dispersion. For the methanol, we've got dispersion because it is all nonmetals, so it's covalent. It's also asymmetric, so we've got dipole-dipole. And if you look on the OH group, that hydrogen is attached to that oxygen, which means we have hydrogen bonding. So because this molecule has more intermolecular forces, it's going to have the higher boiling point between these two. The next pair is a water molecule. So water is going to be covalent. And if I cut it in half, it's different on both sides. So it's dipole-dipole. And I have H attached to F, O, or N. For the other compound, it's made of all nonmetals, so it is covalent, and we have dispersion. And it is also polar. If I cut it in half, it's not the same on both sides. And the electronegativity difference between sulfur and hydrogen is big enough that we get a polar molecule. But there's no hydrogen bonding because those H's aren't attached to F, O, or N. So even though these two molecules look very similar, the water is going to have a higher boiling point because it has more intermolecular forces. Next set of questions are all naming. So here's the rules. We've got ionic compounds, which are going to be a metal and a nonmetal. You name the first metal, and if it is transition, you need to use Romans to show the charge. You name the second nonmetal. You name that by changing the ending to "ide." And if there is a polyatomic ion, you just have to rewrite the name. In the case of a covalent compound, which is going to be all nonmetals, you write the name of each element, change the second element to end with "ide," and you want to use the prefixes to indicate how many of each element that are present. The exception there is that you never start with mono. So even if the first atom has only one atom, then you're not going to write mono. You're just going to leave that out. For acids, we need to look at the thing that isn't hydrogen and look at the ending of that. And if it's "-ide", we're going to name it as a hydroblankic acid. If the ending is "-ate", we're just going to name it blankic acid. And if the ending is "-ite", we're just going to name that blank-us acid. So first one, I've got Cu2SO3. So in order to name this, we're going to name the pieces. So first thing that we have is the Cu, which is copper. So we know that that's copper. Copper is a transition metal, which means I got to figure out what its charge is and then put that in Roman numerals. I don't know the charge on copper, but I do know the charge on the other thing. The other thing is sulfite. So I'm going to write sulfite because we know that part. Sulfite, SO3, is a polyatomic ion. So we can check our polyatomic ion sheet. And we see that for sulfite, the charge is -2. So that means in order to balance it, my total positive charge must be +2. So I'm trying to get a positive charge of +2, and I've got 2 coppers because it's Cu2SO3. So that means each copper has to be +1. So in my name, I got to indicate the charge on the copper as 1. Copper 1 sulfite. Next is lead-4 chloride. So once again, we've got another ionic compound. The first one was also ionic. We've got lead, which is Pb, and 4 chloride. So that 4 is telling me the charge of the lead. Not how many, it tells me the charge. Chloride, before I changed the ending, used to be chlorine. So chlorine is Cl, and it's got a charge of -1 based on its position on the table of elements. So because the lead is +4, I have to have 4 chlorines to balance that out because that will give me a -4 charge. So each chlorine has a -1 charge. There's 4 of them, so that gives me -4, which balances out the +4 on lead. So my formula is just going to be PbCl4. And these were both ionic compounds. Next I have Na3PO4. So Na3, sodium, is a metal, and PO4 is a polyatomic ion. So this is going to be an ionic compound. So let's name the first metal. So Na is sodium. And this is not a transition metal, so I don't need Romans. You know the charge of sodium just because it's in the first column of the table of elements. So I've got sodium, no need for a Roman numeral. The next thing is a polyatomic ion, so whenever we come across those, we just rewrite their name. So sodium phosphate. Next problem is sodium sulfide. So sodium is a metal, and sulfide, before we change the ending, was sulfur. So I've got a metal, sodium, and a non-metal, sulfur, making this ionic as well. So got to worry about charges. So sodium is Na, and it's in the first column, so it's +1. And sulfide used to be sulfur, and sulfur has a charge of -2. So I've got a -2 charge on the sulfur side and only +1 for sodium. So I need 2 sodiums. So each sodium is +1. 2 of them makes a positive charge of +2, which balances the charge on the other side with the sulfur. So my formula is just Na2S. Next, I've got NH3. So nitrogen is a nonmetal and hydrogen is also a nonmetal. So this is going to be a covalent or molecular compound. So whenever we do that, that's where we have to write the name of each element, change the ending to "-ide, and use our prefixes. So nitrogen, there's only 1 of them. So normally we'd want to write mononitrogen, but we never start with mono, so I'm just going to write nitrogen. And I've got hydrogen, which will become hydride whenever I change the ending, and there's 3 of them. So that's trihydride, tri meaning 3. Next up, I have hydrophosphoric acid, so that's obviously an acid. So that means that I have to figure out what the ending is. So I've got a hydro blank-ic acid. So that's going to match up here to ide. So it means that this was originally phosphide. Which is just plain old phosphorus. So there's phosphorus. We have a element that has a charge of -3. And because this is an acid, it's going to start with H, and the charge on H is +1. So I need 3 hydrogens to balance out this -3. So that gives me +3, which balances out the -3 in the phosphorus. So my formula is just H3P, hydrophosphoric acid. Next set, I've got HC2H3O2. So I've got a bunch of different atoms here. That's a hint that there's a polyatomic ion in there somewhere. And it starts with H. So because it starts with H, that's going to be an acid. So that means I got to look at this part, the thing that isn't hydrogen. And the name of this is a polyatomic ion that's called acetate. So since I have this ATE ending, I'm going to rename this as blank-ic acid. And this is what goes in the blank. Everything but the 8. So no hydro. I'm going to get acetic acid. Next one, we have another acid, chlorous acid. So I got to match the form to the ending. So I have a blank-us acid. So that's going to correspond to the ending of ite. So originally this chlor was originally chlorite. So chlorite is a polyatomic ion, and its formula is going to be ClO2, and it's got a -1 charge. So it's an acid, which means we put hydrogen in front. So my charges are already balanced. So just HClO2 is chlorous acid. Next up, I have nitrogen and oxygen. So because those are both nonmetals, this is a covalent or molecular compound. So N is nitrogen, and there's 2 of them. So the prefix for that is di. So dinitrogen means 2 nitrogens. And then I've got oxygen, which becomes oxide, and there's 5 of them. So that's pentaoxide. Next, I've got silver bromide. So silver is technically a transition metal, but its charge is always +1. So that's just going to be silver, +1 charge. Bromide used to be bromine, and that's just Br, and that charge is -1. So my charges are already balanced, so my formula is just AgBr. Next, I've got PbSO4. So Pb is lead. It's a transition metal, and SO4 is a polyatomic ion. So this is an ionic compound. So let's start out by writing lead, because I know that part. And I don't know the charge on lead, so I can't put my Roman numerals yet. I do know the charge on the other thing, though. So that SO4 is sulfate. Polyatomic ion, we just look up its name. So sulfate has a charge of -2, which means the positive charge to balance that must be +2. And there's only 1 lead, so the charge on that 1 lead has to be +2. So this is lead 2 sulfate. Next I have titanium 2 acetate. So I have a transition metal, and acetate is a polyatomic ion. So this is definitely an ionic compound. So titanium is Ti, and its charge is +2. And then I've got acetate, which is C2H3O2, polyatomic ion, and the charge of acetate is -1. So if titanium is +2, I'm going to need 2 acetates to balance that out, so I get -2. So it's just titanium C2H3O2 acetate, and there's 2 of them. We need that parentheses there because I want to make sure I'm saying here's acetate and there's 2 of them, not C3 C2H3O22. So I need that parenthesis there around my polyatomic ion. Next question is just about summarizing the different bonding types. So first one that we have is ionic. Ionic compound is something that is composed of cations and anions. A metallic compound is going to be the attraction between free electrons in the electron C to metal cations. So we have these metal cations which give up their valence electrons to this electron C, and those attractive forces hold the metal together. Next we have polar covalent and nonpolar covalent. So in polar covalent, that's where the electrons are being shared, but they're being shared unequally. So one atom is pulling harder on those shared electrons, resulting in a region of positive charge and a region of negative charge, which is polar. Nonpolar is where we share, but we share equally. So there's no difference in charge. We have equal sharing of electrons all across. Ionic compounds generally occur between metals and nonmetals. You could also have polyatomic ions. Metallic bonds obviously occur between metals, and covalent bonds are formed between nonmetals. In an ionic compound, one atom is going to give up one or more electrons to the other, which receives them, so they're transferred. In metallic bonds, those electrons are all being shared in the electron C. And in polar covalent and nonpolar covalent, they're being shared, just equally or unequally. So a good example of ionic compound is sodium chloride, NaCl. A metallic bond you might see in something like brass or iron or steel. Brass and steel are alloys, which means that they're mostly iron in the case of steel, or mostly copper in the case of brass, but then they have other things mixed in which give the metal, the alloy, different properties. Polar covalent is water, and nonpolar covalent is oxygen, or any of the diatomic molecules will work because they're highly symmetrical. Number 5 is predicting Vesper shapes of some molecules. So first one I have is HCl. And you might come across this one and get stuck because it asks for the bonding atoms and the lone pairs on the central atom. But I've only got 2 atoms. So the only way to connect 2 points is with a line. So this molecule is linear because there's only 2 atoms. Next I've got carbon dioxide. So in these double bonds there's 4 electrons from each. So my central atom is carbon, and it's got no lone pairs, and 2 atoms are bound to it, the 2 oxygens, which if we check on our Vesper chart corresponds to a linear shape. Next one, NH3. So each of those single bonds has 2 electrons in them, and then nitrogen has 2 electrons that are not in a bond sitting on top. So that means that there are 3 atoms bound to nitrogen, and there's 1 lone pair, which corresponds to the shape of trigonal pyramidal. So we just used that Vesper chart that we saw earlier to figure out what the shape of these is going to be based on how many atoms are bound to the central atom and how many lone pairs there are on the central atom. Next is asking us to use electronegativity to determine polarity. So in order to do that, I need my electronegativity table, and it's nice to have electronegativity differences so we know what range each type of polarity or nonpolar falls into. So hydrogen and chlorine. So hydrogen is 2.1 minus chlorine, which is 3.0. So we're going to take the absolute value because we just want the magnitude of the difference. So that's 0.9. which is going to fall in the range of moderately polar covalent. Next we have H and O. So again, we get a large difference here. So that's a difference of 1.4, which falls in the very polar covalent range. Hydrogen and carbon. So the difference there is going to be a difference of 0.4, and that's right on the fence between moderately polar and nonpolar. So if this was in a molecule and it was all carbon to hydrogen bonds, I would look for symmetry to help me decide whether or not it was moderately polar, just a little bit polar, or completely nonpolar. Next question is asking us to use symmetry to determine if the following are polar or not. So first one, if something is symmetric, it's going to be nonpolar. If it's asymmetric, so if I cut it in half and it's different on the two halves, that's going to be polar. So if I cut water like this, the two halves are roughly about the same. But if I cut it another way, like this, I see that it's different on the two sides. So based on that difference, this is going to be asymmetric and it's going to be polar. In the case of chlorine, no matter how I cut that, it's the same on both sides. So that's highly symmetric, which means that we're going to be nonpolar. For the last one, I've got lithium with a +1 charge and chlorine with a -1 charge. The fact that I have charges tells me that this is ionic. So only covalent molecules have polarity. Ionic is like an extreme case of being polar, where the electronegativity difference is very large. So because this is ionic, I wouldn't say that it was polar. I would simply say that it was ionic. Next question, which will dissolve in cyclohexane? So this is where we're going to use the rule like dissolves like. So if something is nonpolar, like cyclohexane, only something else that is nonpolar is going to be able to dissolve in it. So there's I2 and HCl, NaF, and CO, carbon monoxide. So based on my electronegativity difference, I'm going to get that hydrochloric acid is polar, so that won't dissolve in cyclohexane. Carbon monoxide is polar, and sodium fluoride is ionic. So those are all charged. They're all polar or ionic. So those won't work. So the only thing that will dissolve in the nonpolar cyclohexane is going to be iodine. Because the electronegativity difference is 0, it's nonpolar covalent, it will dissolve in something else that is nonpolar. Next question, if we look at these formulas, some of them are wrong and we got to figure out why. So we're going to use charges to determine that. So potassium has a +1 charge, and MnO4 is permanganate, which is a polyatomic ion with a -1 charge. So my charge is balanced, which means that's good. That one is a correct formula. Calcium has a charge of +2, and PO4 is phosphate, that has a charge of -3. So my charges aren't balanced here, which means this one's no good. So the formula for that should be calcium 3, PO4 2, because this is +2, so that gives me a total of +6, and this is -3, and that gives me a total of -6. KOH, so K is +1. OH is the polyatomic ion hydroxide, and its charge is -1. So my charges are balanced, so that one is okay. Next is NaCl2. So sodium has a +1 charge because it's in the first column on the table of elements, and chlorine has a charge of -1. So I've got NaCl2. So that gives me a minus charge of 2 and a positive charge of +1. So that's not balanced, so that doesn't work. The correct formula is just NaCl. Charges are balanced. We get +1 and -1. Number 10, some of these molecules are named incorrectly, and we've got to figure out which ones. So let's start off with CaH2, calcium hydroxide. Well, this is an ionic compound, and we've got calcium, which has a +2 charge, and hydroxide is the polyatomic ion OH with a -1 charge. So already I know there's something fishy because I've got an H here and an OH over here. So calcium hydroxide, once we balance our charges, is just CaOH2, calcium hydroxide. In this case, I have hydrogen, which is going to become hydride. So this is actually calcium hydride is the correct naming for this. Next one, I have H2CO3. So it's pretty apparent that I have an acid here, and I have a blank-ic acid, which means this carbon was originally carbonate. The formula for carbonate, it's a polyatomic ion, is going to be CO3, and its charge is -2. Because this is an acid, we need to put hydrogen in front. Hydrogen has a charge of +1, so I need 2 hydrogens to give me a +2 charge to balance out the -2 charge from the carbonate. So this formula, H2CO3, matches up the name. Next one, I have iron sulfate. So Fe is iron, and sulfate is a polyatomic ion, so this is an ionic compound. Now, iron is a transition metal, which means this name is wrong because I need to have the Roman numerals which indicate the charge of the iron. So we got to figure out what the charge of this is. So I don't know what the charge on iron is, but I do know the charge of SO4, which is sulfate, and that's -2. So I got to have a +2 charge to balance that out. There's only one iron, so the charge on that one iron must be +2. So the name of this compound is iron 2 sulfate. So this formula, or name rather, is incorrect because there's no Roman numeral here to tell me the charge of the iron. Next up, we have CaOH2, calcium hydroxide. So we already know that calcium is Ca +2. Hydroxide is the polyatomic ion OH -1. So I need 2 of them. So I get -2 and +2. So my formula CaOH2 is correct, calcium hydroxide. This is, by the way, because I have a metal and a polyatomic ion. This is also ionic. Next, I have H2SO3, named as sulfuric acid. So because I have a blank-ic acid, this originally ended with 8. So this was once sulfate. Sulfate is SO4. So we've got a problem there because I've got SO4 and it's written as SO3. So that's not right. So sulfuric acid has a charge of, sulfate is -2. Hydrogen goes in front, which is +1. So sulfuric acid is H2SO4. So let's name this thing correctly. I do know that it's an acid. SO3, the name of that is sulfite, one less oxygen than sulfate. So sulfite, SO3, has also a -2 charge. And I've got 2 hydrogens in front, so that's good, so that balances. So now I got to figure out how to name this. So if I have an ite, that was originally a blank us acid, and the blank was the part that isn't ite. Sulfur's a little weird, so we're just going to write the full name for sulfur. So that's sulfurous acid, not sulfuric acid. Next, I have chromium 2 nitrate. So let's check. The charge on nitrate is -1, and there's 2 of them, so that gives me -2. So my positive charge must be +2, and there's only 1, so charge of 2 is good. Cr is chromium, and nitrate is NO3. So that one is named correctly. KCN, potassium 2 cyanide. So first and foremost, potassium isn't a transition metal. Potassium is in the first column and its charge is +1. So not only is it wrong to have a Roman numeral, but if I did put one, it should at least be +1 because that's not even the right charge. This is saying +2. So I don't need that Roman numeral. Potassium is correct, and Cn is cyanide, and they're balanced and everything, so that's correct. So this is almost named correctly, except I just don't need those Romans, so potassium cyanide. Last one in this set is going to be nitrogen trioxide. So whenever we have it written like this, nitrogen is N, and there's nothing in front of it, so this is mononitrogen, just one nitrogen, and trioxide means O3. So here we see there's a problem. So the correct way to name this is going to be dinitrogen and trioxide, because there's 2 nitrogens and 3 oxygens. Last question is about the Electron C model to explain why metals are going to be malleable and good conductors. So metals are going to be good conductors because the electrons in this Electron C are able to freely flow and carry electric current. So all of these electrons came from these cations. So these are all metal atoms, so they could be like aluminum or something like that. And each metal atom has given up 3 valence electrons to this Electron C. That's given up 3. Everybody's given up 3. So these electrons are flowing around in between these cations. And they kind of act like grease. They prevent any of those positive charges from touching each other, which would cause the metal to break apart. If I hit a metal with a hammer, the cations are going to be able to slide right past each other. And that is again due to that Electron C. So the cations are strongly attracted to the Electron C, and the Electron C lets those cations pass each other when hit with a hammer. So those positive charges never get too close because there's electrons flowing in between them.